Okay, so the last part of this stoichiometry is jazzing it up a little bit. Okay, so in the first type of problems, whether it was limiting reagent or non-limiting reagent, in step 3, you use the flow chart to go from grams to moles. You had to convert everything in moles. The same thing happens with this problem that we're going to describe in a minute. In step 3, you're going to have to find the moles. So it's basically the same procedure. But this is not going to be the situation where you're going to have to use the flow chart. These are going to be problems that involve solutions. And in solutions, you are going to be given molarity and milliliters. From the molarity and the milliliters, you can find the moles. You know, that's what we did in the molarity 2 type of problem, find the moles. So you're still gonna find the moles, but now you're gonna use the concentration, the molarity, and the milliliters that are gonna be given to in a reaction. And so if you look at quantitative analysis or titration, there are 2 types of problems that we are going to address. Titration is the most common one. Gravimetric analysis that involves solutions and precipitates, that's a different one, but the procedure is the same. Balance your equation, change the given amounts to moles, okay? Moles, remember that are the molarity times the liters. Use the reaction to find the limiting reagent if it's necessary. Might not be a limiting reagent problem, might be. And then calculate the moles of the substance that you're interested in. And again, convert the moles into whatever they want you to convert them. Grams, another molarity, or in milliliters, or whatever the case might be. Okay, so the steps are the same. The only difference is when you have to find the moles, this involves the molarity and the liters of the solution. Okay, so it's not just the mole flow chart, it's the molarities and liters. So let's look at what a titration means. I want to change the slide. The titration involves the use of a burette. Hold on, let me go to the next one. The use of a burette, which is the big long glass tube that we used in the lab, in which you are going to put a substance that you know the concentration for. Like we used sodium hydroxide, 0.1 molarity. So we know that concentration. In the flask, in the Erlenmeyer flask, we are going to put the solution, the substance that we want to find information about. In our case, we had vinegar here, right? We wanted to find the concentration of vinegar, the molarity and the percent mass of vinegar in that lab. So here is going to be vinegar and acid, and here is going to be a base. So titration normally, not 100% always, but 99.9% situation of the situation involves an acid-base reaction. An acid-base reaction. Well, whether it's the base in the burette and the acid in the flask or vice versa. Also, in the flask, you are going to add an indicator, which is a substance that changes color based on whether here it's an acid or a base. Normally, if it's an acid, we put phenolphthalein, which is transparent in an acidic environment. The moment you start dropping the base, NaOH, the acid and the base react. Let's say this acid and the base react, and they're gonna make salt and water. But if you drop more base after the reaction reacts stoichiometrically, if you drop more base, you're gonna have these reactants, these products, and extra base in here. If you drop more than what is necessary. Okay, so when you drop more than what is necessary, the base become in excess. You're gonna have excess base in here. So when you have excess base, this phenolphthalein changes color, because if it's in a basic environment, in a base environment, the phenolphthalein turns pink. And you've seen that pink happening when you did your reaction. So when the indicator changes color, you added just enough base to react completely with the acid, and if you continue, it turns the heavier the pink it becomes, means you added more base than what it actually is necessary. Okay, but that's the moment when you stop the reaction, because you know, okay, the acid and the base completely reacted. If I'm adding more base, I'm adding excess reactant. So let's see how a problem like this would look like. The end point in a titration, so this is a text of a titration problem. the end point in a titration of a 50 ml sample of aqueous HCl. So they use big words, but you remember to weed out what you don't need. 50 ml HCl solution. That's what's given to you in the flask. In the flask. So you have your burette here. Pardon my burette. And here's your flask. And this problem says that here in the flask you have 50 ml of HCl. Right? So the end point of this is reached by the addition of 35.23 milliliters of 0.25 molarity NaOH. NaOH is in the burette, and they tell you the concentration of 0.250 molarity. And once you do the titration, the end point is when the color of the phenolphthalein turns, when the color changes in the flask. That means the reaction is done. So the color turned when you had, after you dropped 35.23 milliliters. Okay? And the question is, what is the molarity of the HCl? So they want you to find the molarity of the acid that you put in the flask. So I want you to pay attention to what's given. They give you a molarity and they give you a volume. They give you another volume and they want another molarity. This can be confused with an M1V1 equals M2V2 problem. Do not confuse it. When you have a dilution problem where you can use the M1V1 equals M2V2, you have a situation where you have the same substance that has been diluted. Here you have two substances, sodium hydroxide and hydrochloric acid. So you have molarity and volume for one substance and molarity and volume for a different substance. This is a stoichiometry problem because these two substances react with each other and are completely turned into something else. So the reaction is hydrochloric acid and sodium hydroxide make sodium chloride and water, and the reaction is balanced. All of this is balanced. So we are going to follow the steps. Step 1 and 2 say balance your reaction, blah, blah, blah. Let me write the reaction here. HCl plus NaOH makes NaCl and H2O. Does it matter, the state of matter? Do they matter to me at this point in calculation? No, I'm focusing on calculation. I'm not focusing on writing the reaction the way it has to be exactly. As long as it's written correctly and it's balanced, the state of matters at this point in the math do not matter. So the step is underline what you need and what's given to you. What is given to you? They give you NaOH, okay? They also give you some information about HCl, but what do they want you to calculate? They want you to find the information about HCl. So these are the two things that you're focusing on. Because in stoichiometry, you only focus on two things at the same time. I don't care how many reactant and product you have, you're focusing on two at the same time, okay? So, let's look at what they ask. Find the molarity of HCl. What is the molarity of HCl? Is the moles of HCl divided by the liters of HCl, right? Solution. That's the definition of molarity, the moles of the solute over the liters of solution. When I'm talking about the liters of solution of HCl, how many liters I have? This gives me that information. These 50 milliliters are 0.050 liters of HCl solution, right? So the liters for this molarity, I have it right here. This can be plugged in here. So I need to find the moles of HCl. So to solve the problem, I need to find the moles of this. This becomes my X. Now what is it given to me? Convert the given amounts into moles. That's what step 3 says. Given is molarity of NaOH. Given is milliliters of NaOH. Can I find the moles from this information? Considering that the molarity times the liters are the moles. So when they give me molarity and milliliters, my first thing would be make these milliliters into liters, 0.03523 liters of NaOH. NaOH and find the moles of NaOH as your molarity times the liters. Moles of NaOH, molarity is 0.250, and molarity is moles per liter, multiplied by 0.03523 liters. Cancel your liters, so I don't remember how much this is. Anybody can do the math? 0. Something with an 8. So it's 0.25 times 0.03523. How much is that? Maybe I have it on
0.0017.
Yeah. So 0.008, I got 881 moles. Moles of NaOH. So at this point, this would be your step 3. Step 3, right? Find the moles of what's given to you, and I have the moles of NaOH. So I'm going to find step 4 to calculate the moles of HCl. So what I have given is 0.00881 moles of NaOH. X is my HCl, 1 and 1, the coefficient. So basically, my step 4 would be X over 1 equals 0.00881 over 1. So my X is 0.00881, the same number because the coefficients are 1 and 1. But what are these now? Moles of HCl. So I changed the substance from NaOH to HCl by using the reaction. So the chemical reaction pops in the 4th step, and that's when you go from a substance that you know the moles to something that you don't know the moles for, and you do a calculation. Okay, so that is your step 4. In step 5 says turn the moles of whatever you calculated into the desired unit. The desired unit is molarity of HCl. You have the moles of HCl, so now in step 5, you find the molarity. The molarity are 0.00881 moles. And we're talking about HCl divided by the liters of HCl, which we determined are given to us, 0.050 liters. And that's going to be a 0.176 molarity. So titration is also stoichiometry, as simple as that. But step 3 and step 5 change from finding the moles or using the flow chart to a little bit more of molarity concepts. As simple as that. Good with this? Okay. Okay, so let's stop the video. And we're going to do a little bit more practice.